Hi. So I'd like to thank the organisers for asking me to do this. It's a bit difficult because there are lots of people in the audience who. So I'm going to. So my talk's different to Helmut's talk in the fact that I'm going to be concentrating on generic rigidity. So I'm not going to have so many pretty pictures, and I don't have any models. So there are a lot of people in the audience, or a sizable number, who know already everything that I'm going to say. So my talk is not directed at them, it's directed at, if there are any people who are not so familiar with generic rigidity, which is really a topic in graph theory. So if you're not familiar with this, please, and I say anything which you'd like to ask about, then please interrupt me and we can talk about it. And for the people who do know everything, I'm quite happy for them to make comments, to make it as interactive as possible, as long as the comments are not too insulting. Or to make corrections, because there are bound to be mistakes in what I say. This is par for the course for me. So to start off with, a lot of the stuff is going to be kind of the same as Helmut said, but a kind of different slant on it. So I'm going to be mostly looking at bar joint frameworks. So it's a graph G together with a map from the vertex set of V to a d-dimensional Euclidean space. And we think of it as a straight line realization of the graph in space. So we think of the edges as being rigid bars and the vertices as being universal joints. And the vertices can move in D space subject to the condition that they must preserve the lengths of all the edges. And two d-dimensional frameworks based on the same graph are equivalent if they have the same edge lengths, and they're congruent if the distance between any two vertices is the same. So this is the same as saying that you could get one from the other by an isometry of D space. And the framework's globally rigid if every frame, so the framework GP is globally rigid if every framework which is equivalent to GP is congruent to GP. And it's rigid if it's globally rigid in some small neighborhood. So if there is some epsilon, so that if we have a framework GP and a framework GQ, and they're very close to each other, so within epsilon of each other, then equivalence implies congruence for such a framework. And this is the same as saying that a framework is rigid if every continuous motion of the vertices results in a framework which preserves the lengths of the edges, results in a framework which is congruent to the original framework. So here's an example of a framework which is not rigid, so it's flexible. Here's a framework which is it's rigid, but it's not globally rigid. So it's rigid because the bottom triangle is obviously rigid. And then we have a vertex of degree 2 at the top, which, because the distance of V1 from V4 and the distance from V1 to V2 is fixed, then the position of V1 is almost unique. There are only two possible positions. So if we fix the bottom triangle, because it's rigid, then there are only two possible positions for the top vertex, and the second position is what we get by reflecting the top vertex in the line through V4 and V2. And we can't get from the one position to the other by a continuous motion. So it's rigid, but it's not globally rigid because of this reflection property. So in the second picture, I've done something slightly different. I've actually reflected the vertex V3 in the line through V2 and V4. So to make it globally rigid, we would have to add another edge, another bar between V1 and V3 to stop this reflection. So the decision problem of deciding whether a given framework is globally rigid or rigid is hard. So Sachs showed a long time ago that even for one-dimensional frameworks, global rigidity is an NP-hard problem. And Abbott, who in his MSc thesis showed more recently that rigidity in 2 dimensions is a hard problem. So in 1 dimension, a framework is rigid if and only if the underlying graph is connected. So it's an easy decision problem in 1 dimensions, but in higher dimensions it's hard. So one way to solve this is, I guess the way Helmut does it is he's not put off by this NP hardness. He actually looks at real frameworks and decides whether they're rigid or not. So another way is to actually instead look at generic frameworks. So generic can mean lots of things, but I think the simplest, at least to me, definition is that we assume that the coordinates of all the vertices form an algebraically independent set over the rationals. So this is kind of the strongest definition of genericity, but I think it's what I'd like to work with for this talk. So again, we saw in Helmut's talk that so the equivalence is a set of quadratic constraints on the coordinates of the vertices. So we fix the distance between 2 vertices, and we can think of that as a quadratic constraint. And if we linearize by differentiating, we get a system of linear constraints. And the rigidity matrix is the matrix coefficient, is the matrix of coefficients of these linear constraints. So we have the quadratic constraint that P of U minus P of V is equal to a constant for all u, v in E. And if we think of P as varying with time and differentiate with respect to time, we get P of U minus P of V dot P dot U minus P dot V is 0 for all u, v in E. And if we think of this as a system of equations with unknowns, which are the derivatives, or the infinitesimal velocities of the vertices, so we think of these as the unknowns, and we think that we're given the framework GP, then these give us the coefficients of the unknowns. And this is a system of linear equations with, we have one equation for each edge. So the number of equations is the number of edges. And the number of unknowns is well, for each vertex we have d unknowns if we're in d-dimensional space. So the number of unknowns, the number of variables is d times the number of vertices. So the matrix of coefficients is this A times D mod V matrix. And in fact, we can write this system of equations as RGP dot P dot is 0. So here's a small example. So we have this 4-bar mechanism, and its rigidity matrix has 4 rows, and I guess if we're in 2 dimensions, it would have 8 columns. So each of these things would be 2-dimensional vectors. Is that okay? So each vector in the null space we call an infinitesimal motion of the framework. Except here I've labeled them as Q rather than P dot. And we think of the vectors Q of V as instantaneous velocities for particular vertices. So for any framework, we're going to have solutions to this system of equations. And we get solutions from the continuous isometries of d-dimensional space. So from the rotations and translations. So we can get actually d plus 1 choose 2 independent solutions to this system of equations. So we can, if we're in D space, we can get D independent translations and D choose 2 independent rotations. For example, by rotating about, I guess, a D minus 2 dimensional subspace given by D minus 2 of the coordinate axes. So this tells us that the rank of the rigidity matrix is at most d times the number of vertices. So the dimension of the null space is at least d plus 1 choose 2. So the rank of the matrix is at most the number of rows, which is d times the number of vertices minus the dimension of the null space. And if we have equality here, then this framework will be rigid because it tells us that every infinitesimal motion is coming from an infinitesimal isometry. So it's not changing the distance between any of the vertices. So we said the framework's infinitesimally rigid if equality holds. So if the dimension of the null space of this matrix is as small as it can possibly be. So the only infinitesimal motions are infinitesimal isometries. So infinitesimal rigidity implies rigidity, but it's a stronger condition. So So we've seen that this is a rigid 2-dimensional framework. So I could put a piece of string between these 2 vertices, and I could put a vertex on this piece of string. And because this is rigid, then this string will be pulled tight in any realization, any equivalent realization. So this will be rigid. But it's not infinitesimally rigid because there's a kind of obvious infinitesimal motion, which I get by giving this vertex an infinitesimal velocity which is perpendicular to this line, and then keeping all of the other vertices fixed. So that's an infinitesimal motion because the dot product of this times the 0 vector, minus the 0 vector is orthogonal to the difference between the position vectors of these 2 points. So this is an infinitesimal motion. It's an element of the null space of the rigidity matrix, but it's not an infinitesimal isometry. So the infinitesimal isometries are just combinations of rotations and translations. And translations move everything, and rotations keep at most one point fixed, whereas this is keeping 4 points fixed. So infinitesimal, in general, infinitesimal rigidity is a stronger property than rigidity, but Asimov and Roth showed in 1979 that actually these two properties are equivalent if P is generic. So we don't actually need algebraic independence for this. We just need that P is a point at which the rigidity matrix achieves its maximum value. So because the entries in the rigidity matrix for a generic realization are algebraically independent, we can think of them as being variables. And that means it doesn't matter what actual values they take, as long as they're algebraically independent. So the rigidity of a generic framework only depends by which edges exist or not. So it only depends on the graph G. So as long as P is generic, it doesn't matter which generic point we choose. So so I'm originally a graph theorist, and so this is kind of very appealing for me because it means generic rigidity is equivalent to a problem about graphs. So I guess many people here are geometers, and that's not very appealing to them. But as a graph theorist, it's very appealing to me.
So I've got a question. If you have weaker notions of genericity, does that statement still hold or not? So for example, if you take just the generic notion of maximality of the rank of the rigidity matrix, does it still hold that you can just look at the graph?
In a sense, yes, but then you have to decide how do you know that this point is the maximum rank of the rigidity matrix? But yeah. As long as you're, I was going to say lucky, but actually you'd be very unlucky to land at a point which is not the maximum rank of the rigidity matrix, so far. So thinking about this in terms of graph terminology, so I'll say a graph is independent in d-dimensional real space if the rows of the rigidity matrix are linearly independent for any generic GP, for any generic framework. And so if they're independent for some generic framework, they're independent for all generic frameworks. In fact, if they're independent for some framework, then they're certainly independent for all generic frameworks. And similarly, we say that G is rigid if some framework has... oh, this is wrong, eh? So I corrected the slides yesterday. So this should be D mod V minus D plus 1 just tau. And if we can determine independence, then we can determine rigidity. And that's just because of the Grady algorithm. So if we want to work out the rank of a matrix, we can choose some row, which is not the zero row, and then we can check and see if there's a row which is linearly independent from it, and if there is, we can choose that. And if there's a row which is linearly independent from it, we can choose that, and we keep on going until we've got a maximum set of linearly independent rows. And because any set of linearly independent rows extends to a maximum set of independent rows, if we can test for independence, we can work out the maximum rank. So independence and rigidity are algorithmically equivalent for generic frameworks.
Can I interrupt you again?
Yes, please.
Do you know of any algorithm that is in the Turing machine model to determine rank maximality or to determine the exact rank of the matrix? I don't know, man. I mean, in other machine models, yes. But as soon as you got something to do with, with floating point numbers, all that's wrong. Especially if they're not even algebraically dependent.
So I'll say, Mira would like to say something, so I'll say something first. So why can't you just, so you can work out...
How do you represent real numbers?
So I wouldn't, I'd represent them as variables, and then I'd use Gaussian, this is a silly approach, but I'd use Gaussian elimination on the matrix, and I'd get these enormous entries in the matrix.
Okay, so your matrix is in, the length of the edges are in rational numbers.
I would put them in variables, I think, if I was looking at generic rigidity. But that would be an algorithm.
I'm not sure how the components of the numerical components of this matrix would be represented.
If you are looking in integer for a number,
Yeah.
so you are no longer in generic statement.
Exactly.
Yes. So therefore,
Yeah.
Yes, please, Mira.
So if you allow randomized algorithms, if you allow randomized algorithms in the Turing machine model,
Yes.
just look at the rigidity matrix of any determinants,
Yes.
right? And then you try to determine from that to ensure that it does not humongous polynomial with high degree,
Yeah.
but you use Schwarz's algorithm,
Yeah.
which is a statement program, so you can tell whether it's identically zero, whether if it is identically zero, if it is not identically zero, with high chance you find a non-proof.
But if I don't have a deterministic algorithm, then I should just plug any kind of numbers and then
You have a little bit of proof to be done.
basically, if you ask a question of, how to say, finding rational points or correct,
But I guess the random algorithm, so what I'd like to do is I'd like to understand the structure which makes a graph generically rigid. So the fact that given a graph, I can put a random algorithm and it'll tell me whether it's rigid or not is not telling me anything about the structure that's making it rigid. So we'd like, as I said, we'd like to understand what generic independence or generic rigidity means for graphs in D space. And a long time ago, I guess, Maxwell came up with the necessary condition for independence. So the necessary condition is just based on the fact that the dimension of the null space of the rigidity matrix is at least D plus 1 choose 2. So if I have a graph which has more than D mod V minus D plus 1 choose 2 edges, then its rows must be dependent because it's got more rows than its rank. So the rank is bounded by D mod V minus D plus 1 choose 2. And the same is true for any subgraph. So if any subgraph has too many edges, then the rows in that subgraph are linearly dependent. And in fact, this condition works for when D is equal to 1. So for D equals 1, it's just telling us that the number of edges induced by any subset is at most the number of vertices in the subset minus 1. So it's telling us that the subgraph is a forest. And Maxwell's condition also characterizes independence when D is equal to 2. So this is a celebrated theorem of Laman, which probably started people thinking about rigid graphs, I guess. Thinking about generic rigidity. So Laman showed in 1970 that Maxwell's condition characterizes independence when D is equal to 2. And So the fact that we're working with a matrix, so we have the rigidity matrix, and the rows are labeled by the edges. Gives us a matroid on the edge set of a graph. So for any D. A matroid is a collection of, it's a ground set, which is the edge set of the graph, together with a collection of subsets, matroid M. So I have my graph G, which is VE, and I'm going to have a matroid on the edge set. This is the ground set, and then I have a collection of subsets of the ground set which are independent sets. So I refer to the subsets in I as independent sets. And the independent sets in my matroid are the sets of rows which are linearly independent in their generic realization. So this gives me a very kind of elementary but beautiful structure called a matroid. And we can use the theory of particular of Jack Edmonds to show that Laman's theorem, so Laman's theorem gives a good characterization for independence, but it also gives a good characterization for what a generic rigidity is for graphs. So this was pointed out by Lorbas and Yemeni, and it uses the idea of a cover of a graph. So a cover is a family of subsets of the vertices, so that every edge belongs to at least one set in the family. And the Lorbas-Yemeni theorem tells us that in order for a graph to be rigid, then this inequality must hold for all covers. So the idea is that so I have my edge set A, and then I have some cover of the edge set. Is it T? I don't know. And so in order to be rigid, the graph must have twice the number of vertices minus 3 independent edges. So the rank of the rigidity matrix must be at least twice the number of vertices minus 3. So I must be able to find twice the number of vertices minus 3 independent rows in this matrix. Or equivalently, I need to be able to find a set of twice the number of vertices minus 3 independent edges in this matroid. And now in any subset, the maximum number of independent edges I can get in this subset is twice the size of x1 minus 3 by Maxwell's condition. And similarly, the maximum number of independent edges I can get in this subset is twice the size of x2 minus 3. So any cover of the edges of the graph gives me an upper bound on the size of a maximum independent set of edges. So in fact, the fact that I can find twice x1 minus 3 independent edges here and twice the size of x2 minus 3 independent edges here, it doesn't tell me that when I take the union of these independent sets, I get something which is independent. So it's not. So it's an obvious upper bound, and I guess the difficult part is showing that it's actually tight, that it's a necessary and sufficient condition. So if a graph is rigid, is that the real way around? Sorry, if a graph is not rigid, then I can find some cover of the vertices so that this inequality fails. So here's an example of how you would use a cover in 2 dimensions. So I'd like to show that, so it's clear from anybody with any intuitive geometrical sense that this graph is not rigid in 2 dimension in the plane. But we can use covers to certify that fact. So if I let x1 and x2 be the complete graphs on 4 vertices at either end of the graph, and x3 and x4 to be the edges, or the end vertices of the edges joining the 2 K4s, and we work out this sum, we get 12, which is less than twice the number of vertices minus 3. So it tells us this is not rigid in R squared. And a graph theorist can do this without any geometric insight. Is that okay? So the big open problem in the area is try to characterize generic rigidity in 3 space. And this famous example called the banana graph shows that Maxwell's condition is not sufficient in 3 space. So Maxwell's condition for independence is that any set of at least 3 vertices should induce 3 times the size of the set minus 6 edges. Is it construction or is it a cleaner? Oh, the windows are probably what? They're open. Hello, we're trying to give a talk in here. What? We're trying to give a talk in here. Well, it's not going to make much difference, is it?
I don't know. At least it won't slap. Can we close the window at least? Can we close the window? At least it won't slap.
Thank you, Leo. Nah, if it was open, I'm sure he would have stopped. He thinks it's all right now.
Damn it.
Maybe we could ask him to have an early lunch.
It was the one above that I was
Jetzt, dass Sie 10 Minuten später erst das machen. Also in 10 Minuten sind wir fertig.
Thank
10
you.
minutes left.
10 minutes left? So this is a graph, it's called the banana graph. And if you forget about the dotted edge in the middle, it's got 18 edges, which is the right number to be rigid. So if it was independent, then it would be rigid. But it's clearly not rigid in 3 dimensions, because the dotted thing acts like a hinge, and this thing can swing on the hinge, so it's not rigid. So it is not independent. So that's a geometric reason why it's not independent. And if you check, you can check that any set of vertices induces at most 3 times the the number of vertices minus 6 edges. So it shows that Maxwell's condition, which is necessary for independence, is not sufficient in trace space. So there's also a slightly more sophisticated argument using covers. And the idea is that we add the dotted edge to the graph. So we add the edge v1, v2. And then we have a cover which can... So once we've added that edge, the graph is the union of two complete graphs on 5 vertices, which have v1 and v2 in common. And so the maximum number of independent edges, if you do Maxwell's count, in a complete graph on 5 vertices is 9. So we can have maximum number of edges of independent edges on the left is 9, and the maximum number of edges on the right is 9. But now we do something kind of subtle, which is in each K5, we can choose an independent set which contains the edge v1, v2. So if this graph were independent, then this edge v1, v2 would extend to a maximum independent set. And on the left-hand side, it contains at most 9 edges. On the right-hand side, it contains at most 9 edges. But they've got this edge v1, v2 in common. So this maximum independent set in this graph has at most 2 times 9 minus 1, which is 17 edges. And it's got 18 edges, so it's dependent. So we're using the fact that any independent set of edges can be extended to a maximum independent set. So Dress conjectured that actually we could use covers to certify independence, or to decide whether a graph was independent even in 3 dimensions, using this idea of so I guess in the previous side, we think of v1, v2 as a hinge. So if we have a cover, then we say the cover's too thin if any 2 sets intersect in at most 2 vertices. And so the idea is that these sets are going to be rigid subgraphs. And if you had 2 sets intersecting in 3 or more vertices, and there were rigid subgraphs, then the union would be rigid, so that there'd be no point if we were going to pull the graph apart into rigid subgraphs. So we look at 2 thin covers, and we count the number of hinges between the sets in the cover. And so Dress conjectured that we have this sum over all subsets of the cover of f of x, which is like the Lovász-Jemeny theorem in 2 dimensions. So f of x is an upper bound on the number of independent edges that we can have in x. And if the size of x is at least 3, then it's the Maxwell number. It's 3 times the size minus 6. If the size of x is 2, then it's a kind of trivial bound that if I have 2 vertices, then the number of independent edges they can induce is at most 1. So it's slightly stronger than this 3 mod x minus 6 bound, which would be 2 in the case when the size of x is 2. So Dress conjectured that, and then there's this correction term, which is the number of hinges in the cover. So Dress conjectured that if a graph was going to be rigid in 3 space, then this inequality should hold, and it would also be a sufficient condition. So the easy part of that should be necessary, but together with Tabor, we showed that is that right? It's not even necessary. Yeah. So it's necessary, if we have a cover, such that the hinges are independent. So if the set of edges that belong to the hinges, even if is independent in trace space, then Dresser's bound is a necessary condition for rigidity. But Dresser's conjecture is supposed to apply to all covers, and if we look at all covers, there's a problem that we can have way too many hinges. So in fact, there exist covers for which the second term is bigger than the first term. And so for large graphs, the left-hand side, if we minimize the left-hand side over all covers, is going to be negative. So on the other hand, if we just restrict the covers for which the set of hinges is independent, then this condition is not strong enough to rule out many graphs which are not rigid. So I guess there have been several attempts to try and modify Dresser's conjecture to come up with something which is at least which looks reasonable, but I don't think that there is anything around. And so the idea is that the thing on the left-hand side of this inequality should be the rank function of a matroid. And in particular, it should be submodular. So if we minimize the left-hand side, we should have a submodular function. So I think it would be a big step forward if somebody could come up with a submodular function, which was give a necessary condition for rigidity. So how's the time going? So 10 minutes. So I'd like to talk about global rigidity, unless the guy with the sander comes back. So global rigidity is, as you remember, rigidity is about continuous motions, whereas global rigidity is we look at the set of all equivalent frameworks, and that it's actually globally unique. So apart from congruences in day space. So we investigate global rigidity with a different matrix, which is due to Bob Connelly. So a stress, we have the idea of a stress from a framework. So this is a weighting that we put on the edges with real numbers, such that if we work out this sum over all the edges, we get the zero vector. So we weight the direction vector between which represents any edge, and we sum that over all edges, and that should sum to the zero vector. And the associated stress matrix, so rather than being an A times D mod V matrix, it's actually a mod V by mod V matrix. So I put n by n there, so n is the number of vertices. And the entry corresponding to an edge is minus its stress value. Now, the entry corresponding to a non-edge is 0. And then I would like the rows and the columns of this matrix to sum to 0. So the diagonal entries are chosen such that we have 0 row and column sums. So here's an example of a complete graph on 4 vertices in a square. And this is an example of a stress. And this is the corresponding stress matrix. So Connelly showed in 2004. So this is a necessary and sufficient condition for global rigidity. And one part is due to Connelly, and the other part is due to Gortler, Healy, and Thurston. So Connelly showed that the rank of the stress matrix is at most n minus d minus 1 for all stresses, and that if we have a generic realization which has a stress, so that its stress matrix has this maximum possible rank, then this generic realization is globally rigid. So it's a bit like the sufficient condition for infinitesimal rigidity using the rigidity matrix, except this is using the stress matrix. And Connelly conjectured that the reverse implication was true, that if it does not have such a stress with a full rank stress matrix, then it's not globally rigid. And that was proved by Gortler, Healy, and Thurston in 2010. So this gives us, it puts global rigidity in some sense on the same footing as rigidity, in that there is a matrix condition for generic global rigidity. But again, this is it's not clear how, there's no good algorithm to work out this, the rank of this matrix, because it's a matrix with the stress for a graph which is positions are indeterminate, so the stress will be indeterminates. But again, it depends, it's not so obvious, but it shows that global rigidity depends only on the graph and not the particular generic realization. So we can say a graph is globally rigid in day space. So the challenge is to try to characterize graphs which are globally rigid in day space. And a student of Bob Connelly's, Bob Hendrickson, came up with this necessary condition for global rigidity. So for a graph to be globally rigid, it should be, in day space, it should be day connected. It should be day plus 1 connected, because if it has a small vertex cut, a vertex cut with less than or equal to day vertices, then that acts like a hinge in day space. And we can rotate part of the graph about the day vertex cut. And the other condition is that it must be redundantly rigid. So the graph minus any edge should be generically rigid in day space. And the kind of intuitive idea behind that is that if we have an edge whose deletion destroys rigidity, then when we delete that edge, the framework, the generic framework, becomes flexible, and we can move it to another position such that the distance between the two endpoints of the edge is the same as it was originally. And so this gives us another realization which is equivalent but not congruent. And when day equals 1, these necessary conditions, again, they're also sufficient. So when day equals 1, it has to be 2 connected, and redundantly rigidity just is actually 2 edge connectivity. It says if you delete any edge, it stays connected. So it's implied by 2 connectivity. So Bob Connelly showed that when day is greater or equal to 3, Hendrick's conditions were not sufficient to imply rigidity. And in 2005, Thibaut Jordan and myself showed that the remaining open case, which was day equals 2, Hendrickson's conditions are both necessary and sufficient for generic global rigidity. And so one last, so it's a big open problem for day greater or equal to 3 to characterize generic global rigidity, and particularly for day equals 3. So Shinichi Tanigawa proved in 2015, he gave a condition which looks a bit like redundant rigidity, but it holds for all D. So he showed that rather than, if it's kind of vertex redundantly, if a graph is vertex redundantly rigid, so if a graph is rigid and I delete any vertex, it stays rigid in D space, and that holds for all vertices, then the graph is globally rigid in D space. So it's kind of surprising result because we don't know what rigidity means in D space, but still, we know that if it's redundantly vertex rigid, then it's globally rigid. So I don't know. So I thought I'd finish off by talking about some different kinds of frameworks. So maybe I'll talk about a couple and then we'll call it a day.
I think the guy went to lunch.
So I have to use the bucket, do I? No. So oh no, there's boards behind, eh? Ah. So this is a different kind of framework. So the idea is that we have rigid bodies in D space. So the bodies are D-dimensional rigid bodies. They live in D space. And then we join them by bars. And the bars fix the distance between the two endpoints of the bars. And again, the endpoints act like universal joints. And we would like to know when such a framework is generically rigid. So for these frameworks, there is a complete characterization of generic rigidity and global rigidity. So in 91, Tay characterized generic rigidity for body bar frameworks, and Connelly, Jordan, and Whiteley in 2013 characterized global rigidity. So to be rigid, they need to have the property that if we that the underlying graph has D plus 1 choose 2 edge disjoint spanning trees. So if we're in 3 space, so the underlying graph here is so the underlying graph, we have a vertex for each body and an edge for each bar. So we need to have 6 edge disjoint spanning trees. So I guess 1, 2, we need another edge. Eh? So I guess this is generically rigid in 3 space. So if I take out any edge, it's not generically rigid. Or if I, instead of putting this bar here, I decide to put it here, then it's not generically rigid. So it's a surprisingly simple condition for generic rigidity in D space. And then Connelly, Jordan, and Whiteley showed that it's a kind of, there's a Hendrickson condition. So now we know what generic rigidity is. There is a Hendricks condition, which is a necessary condition for global rigidity. So it's globally rigid if and only if it's redundantly rigid. So I guess to make this globally rigid, so this is only just rigid. If I delete any bar, it won't be rigid anymore. So I need to add another bar to make it redundantly rigid. And again, I lose if I put a bar here, because then if I delete this bar, it's not. Oh, sorry. This was the rigid one. So I lose if I put a bar here, but I guess if I put a bar here, it will be globally rigid. So now it has the property that if I delete any edge, I have 6 edges showing spanning trays. So just to give you a flavor of what other kinds of frameworks are, there are direction length frameworks. So in a direction length framework, there are 2 kinds of edges. So there are ordinary length edges, which fix the distance between any 2 vertices. And then there are direction edges, which fix the direction between any 2 vertices. So they fix the... Sorry? They fix the slope of the line joining the 2 vertices. So the slope is fixed, but the vertices can still translate, or the distance can increase as long as the slope stays the same. And for these vertices, for these frameworks, there is a characterization of generic rigidity due to Rigidity, Servatius, and Whiteley. And so for a while, I guess, with Tibor and with Peter Kivash and with Katie, worked on the problem of trying to characterize generic global rigidity for these frameworks. And we kind of almost got there, but not quite. So there's no equivalent of the stress matrix condition for global rigidity. So we don't know that global rigidity is a generic property for direction length frameworks. But what we can prove is we can characterize mixed graphs. So these are graphs with direction edges and length edges, with the property that all their 2-dimensional generic realizations are globally rigid. But there may exist graphs which such that they have some generic realizations which are globally rigid and some generic realizations which are not globally rigid. We don't think they exist, but we can't prove they do. And the final kind of framework I'm going to look at is a point line framework. So a point line framework, we have a collection of lines, let's say in 2 space, and we also have some points. And we have 3 different kinds of constraints. So we have, we can fix the angle between 2 lines, or we can fix the distance between 2 points, or we can fix the distance from a point to a line. So this is a point line framework with 2 angle constraints and 5 distance constraints. And I guess together with John Owen, we managed to characterize when a point line framework in 2 space is generically rigid. Well, I guess this version characterizes independence. And it's kind of interesting, at least to me, that the condition for independence is complicated, but it's a kind of cover condition. It's a partition condition, and there seems to be no simpler condition for independence. So with 2-dimensional rigidity, there is a simple condition for independence, and then there is the cover condition for rigidity, which is the Lovász-Gemini theorem. So for point line frameworks, there's no. This is just the rank function. This is the condition for for independence and rigidity. And the independence problem is not any simpler than the whole thing. And global rigidity generic global rigidity of point line frameworks is completely open. So I'd like to stop there.
Any questions?
So I'm interested about the point-line framework. So the question is it possible to create a usual framework which replaces all those conditions for angles and distances from points to lines? So you can plug a usual point framework which has the same realization space as that one, has the same rigidity.
You mean a framework where you just have points and...
With just points and distances, maybe more points that you have there.
Yeah, maybe. I don't know. It would be nice. I don't know. So we do turn this into a graph with just points, but with two kinds of points. So we have a point corresponding to each line and a point corresponding to each point, and then we represent each constraint by an edge. But so that's not, that just looks at, that treats all the constraints in some sense the same. And if we thought of this as just being distances, so if we imagined that there was only one kind of vertex, so if we imagined this as being a bar joint framework, it would be rigid. But as a point line framework, it's not rigid. So it's not rigid. Yeah, I know it's not what you mean. So it's a bad answer to a good question.
So you can think of bar joint frameworks with some colinear points as maybe modeling what the question says.
Oh, that's true. I forgot about that. Thanks, Tony. So I completely forgot. So I have a paper with Tony and Bernd and Walter and Shinichi Tanigawa and Yasak Eftikan, in which we show that you can model it as a point, as a bar joint framework, in which the points corresponding to the lines are all collinear. So there is a transformation from a point line framework to a bar joint framework with non-generic realization, in which all the lines are all the points corresponding to lines are collinear. Thank you, Tony.
Mira?
So, what would you consider a good characterization of rigidity?
Well, if Jack was here, he would tell me that I should say good in the sense of Edmonds. So what I mean is that there is a theorem which says that a graph is rigid in three space, say, if and only if some condition. And I can use this theorem to, if a graph is rigid, I can convince you in polynomial time that it is rigid. And if it's not rigid, I can convince you in polynomial time that it's not rigid.
And so that's NP intersect point.
Yes,
Okay, so NP intersect point is what you would consider.
as a good characterization, yeah.
You also mentioned that if you have a submodular function which is a necessary condition for rigidity, where would that fall in a good spectrum?
I think it would be independent, but if you, I guess it's just frustration that there are lots of plausible conjectures using covers for what the rank function would be in 3 dimensions. But none of these if it is going to be a rank function, it has to be submodular. So that's the first step. So it seems very difficult to show that any of these conjectured rank functions are submodular.
But what if there is a submodular function which is an optimum and beats all the other existing ones, which are not submodular? They're still optimum.
And there are no examples which show that it's not.
Yes.
Yeah, that would be nice.
Okay, so maybe we should stop the loop. So let's thank Bill again.